Hello. So today we'll be talking about pathfinding. Jerry and I will discuss a well-known algorithm called bug. Bug helps us avoid obstacles when we are trying to head towards a known location or direction. So say we're headed towards that target here, and we are here. Can you see my board on the Zoom, just to double check?
I can see you've drawn two dots on the screen.
Beautiful. Okay. So, and say you have an obstacle in between. So first thing that one might try is we simply keep walking towards the goal. Then we hit the obstacle, and then we choose some direction to stick to the obstacle. And then once we can walk back towards the goal, we just walk there again. This works most of the time. However, there are cases where it could not help us. It could not end up with us reaching the goal. Let's see such an example. Say we have like a more contrived obstacle, something that looks like this. Say the goal is something somewhere here. Oh, that looks cute. And say we are somewhere. Oh, so somewhere here, and say we start right here. So we head towards the obstacle. That is the goal, and then we hit a wall, and then we can't reach we can't walk towards the obstacle, so we follow the wall in that direction, and then we walk this way, and then we're back to the obstacle, so we follow in that direction, and then we keep going in a loop back to the start. So this clearly would not work. If we had turned the other way, maybe it would have worked in this case, but there would still always be this sort of problem where depending on which way you would turn, there could be a cycle. And Jerry is going to show us how to deal with that problem.
Yep, I'm going to jump in here. Give me a moment. So what Mark just showed you was the algorithm known, which we like to call bug zero. So the idea of bug zero, just as Mark mentioned, was you essentially, whenever you hit an obstacle, you essentially pick some direction and keep on trying to go around it until you can find that you can go in that direction again. So I might actually draw out that example again. Miraculously, my writing stylus has crashed or thrown a game action exception or encountered some other form of anomaly, and I'm not actually able to write with it anymore. So you'll have to deal with the marvelous handwriting that comes out of my finger. So essentially, so as Mark presented in bug zero, the fundamental idea was that you would have some starting location which is where you currently are. You have some goal location where you want to go towards, and you have some obstacle in the middle. And whenever you went towards it, you would, whenever you can, you would want to go always towards the end location, because if you know that's the best direction you can go towards, then you obviously want to actually continue going in that direction. The problem is when you do hit that obstacle, then obviously going forward in that direction is no longer an option. But the idea is to simply try to go around the obstacle or do something until moving in the forward direction is possible again. So you would do something that allows you to go around it, something like this. And then once you can see that moving towards the goal location is possible again, you would start sort of going forward towards the end again. But as Mark showed, that exist potentially nasty obstacles that make bug zero potentially not so nice to work with. So what we're going to be working on next is an alternative solution. which is sort of like an upgraded version of bug zero, which is able to guarantee that at least even if the obstacles we get aren't the nicest, we will still be able to guarantee that we actually hit the target location. I'm going to emphasize here that we're still working in a space right now, which is where we specifically are dealing with every location is either completely passable or completely impassable. So you can think of it as like zero rubble versus infinite rubble. And we'll come back and talk about how to bring this back to a space where you can have continuous values of rubble a bit later. But for now, we are dealing with rubble where essentially every location you are either okay with being there, or every location is something that is a location where you don't want to be there. So what we're going to be looking at next is a solution to that pathological example, which is going to be what we call bug one. So bug one is going to be, I'm going to preface this by saying that it's an improvement over bug zero, in that it is able to actually, so the good thing about bug one, so the good thing is that it actually guarantees that you hit the target location. The bad thing is that it can be slower. And so this is a bit of a trade-off that you're working with. And as it turns out, we will actually come back and see later how perhaps there is another aspect of bug zero that we can also trade off that makes it actually perhaps even able to compete quite nicely with bug one. But that's something we'll come back and discuss in a bit of a moment. But the fundamental idea of bug one is that we're actually going to do something different that lets us get around the problem with bug zero, where bug zero sort of like is able to sort of do things that work, but sometimes don't actually work. So what we're going to do is we're going to notice that bug zero is inherently what we call a greedy algorithm. It is actually very greedy. The idea of a greedy algorithm is that it is really making what appears to be the best choice right now. So the idea of a greedy algorithm is that it's greedily making the best choice right now, even though it could come back and harm you later. Like when you're being greedy, quite possibly something will come back to bite you later. And so you'll notice that algorithms such like bug are really different to perhaps other pathfinding algorithms you might have heard of before. Things like BFS, which is like a common shortest paths algorithm, or Dijkstra's algorithm, which is another type of shortest path finding algorithm, or Bellman-Ford, or your other favorite type of like guaranteed accurate shortest path algorithm. What we're dealing with here instead is an algorithm that is less about being perfectly shortest, but something that is about saying, well, given the information we have around us, what is the best we can do? So you'll notice that the intuition about, well, why do we call these algorithms bug? Like, it's a very strange name for an algorithm. And as you've noticed by now, that like bug zero is a bugged algorithm because it doesn't always work. But the intuition behind calling these algorithms bug is that, well, fundamentally, you're behaving almost as if your robot is a tiny little bug on the screen. And it's only able to see that little bit around it, and it has to make the best choice that it can, given that it can only see that much around it as a little bug on the screen. So given that we're a little bug on a screen in like a really big world and can only see a little bit around us, what is sort of the best thing that we can do? So as you've seen in bug zero, we're sort of like trying to do this thing where we're going around the obstacle, but sometimes we hit the situation where it doesn't work. I'm actually going to draw that. I'm going to draw that example out again, because it sort of thinking about why it doesn't work actually gives us some pretty good insight into how we can fix it and get ourselves into bug one. So I'm going to draw that example out again. So it looks something like this. So we have some obstacle that looks like this. I'm going to briefly shade that in using my lack of a stylus. we had a starting location here, and we had an ending location somewhere in here. And we noticed that the problem with bug was that if we went sort of, let's say we went forward and we got here because we were going towards the goal location, we found that, well, we've hit an obstacle, so we have to sort of like try to go around it. And so we do the thing where we go around it. So let's say we go around to the left, we get here, we notice that we're able to go towards the target again. And then we sort of keep going. We go towards the target. Let's change the color here. Let's say we're going towards the target. We hit another obstacle, and then we start trying to go around it again. But this time when we try to go around it, we start going all the way around the side. And we're back. Whoop. And we're back here again. And we end up inside this ridiculous loop of just going around and around this cycle. Now, if we think about sort of what makes this algorithm not work, so this is bug 0. So we're acting as a little bug. And so after we hit this location here, our bug is like, well, okay, we're in a bad location. We're trying to go around the obstacle. And I guess the idea of going around the obstacle is, I guess if you were a bug trying to go around it, you would essentially want, this is what you would do if you were a bug trying to navigate the world as well, right? Like, you know where you want to go. So if you hit an obstacle, I mean, you can't go above it and you can't go under it. So you've got to go around it. The problem here though, and I think the biggest problem here with what bug 0 has done is that once it gets here and is like, well, I think I'm finished. Bug 0 thinks I have finally found a way around the obstacle because I can see a straight line path towards my goal again. Like, this is great. It gets here and it thinks I have completed my task of going around the obstacle and I can try to continue towards the goal again. But we know that it hasn't actually completed the task of going around the obstacle. Like, if anything, it's actually done a worse job of going around the obstacle than doing nothing at all, right? Because it's actually ended up further away from the goal than when it started. So the fundamental problem with bug 0, big problem, is that it's ended up further away than it started. Oh dear, is my, okay, further away than it started. And I'll give that a moment to sink in. Mark, are there any questions in the chat or anything about what we've said about bug 0 so far?
Doesn't seem like it.
Okay, if you have any questions, you should ask away now, because the next thing that's going to happen is we're going to use this idea to fix bug 0 and give us bug 1. All right. I'll take it that this makes sense so far. So I'm going to go ahead and dive into bug 1. So the idea of bug 1 is that what we're going to do is make sure that when we're going around this obstacle, we never end up further away than we started. Because if we end up further away than we started, then we may as well have not bothered doing this. Like, the only point of trying to go around an obstacle is to actually get closer to the goal. So if we're ending up further away, this is probably a really bad thing. So here is what bug 1 is going to do. The idea of bug 1 is, bug 1 says, instead of just stopping as soon as it's possible to go straight towards the goal again, instead of doing that, because like this as soon as here is what's causing us a problem, right? Like this as soon as might stop us in a place where we're actually in a worse position. So bug 1 is going to say, instead of doing that, we're going to try to find the best location to continue towards the goal. And in here, when we say best, we're going to say the closest point on our obstacle that we can end up at. So specifically, well, let's go through this on an example, because I think examples make this much clearer. So let's suppose, again, that we have let's just do it with one obstacle first, just to see what it looks like. And then we can talk about maybe extending it to another obstacle. But suppose that this is our starting location. This is our ending location. And then we just have one big rectangular obstacle in the middle. Actually, let me just move things around a bit so that we have a bit more space. So let's just move that. Let's move that here. Let's move that down a bit. All right, just so we have some space to play around with things. Cool. So what bug one is going to say is, well, okay. Bug one is going to start at the starting location, which is the green dot down the bottom. It's still going to walk towards the goal. It's going to walk towards the goal because that's the optimal thing to do. But now it's going to hit that obstacle and it's going to realize that, you know, this is not a good place to be. I've hit an obstacle. I can't go forwards anymore. So I have to find some way around the obstacle. And so it's going to do the same thing as bug zero. It's going to start trying to go around the obstacle. So I'm going to write this on the side, actually. So I'm going to annotate what each of these colors mean. So pink. So this line is walk towards goal. So walk towards goal. And now the second thing that's going to happen is it's going to start trying to go around the obstacle, just like bug zero. So you're going to start going around, and it's going to continue going around. And let's suppose it gets here. And this is the point where bug zero is going to say, okay, I can see the goal again. So I'm going to just stop going around the obstacle and go towards the goal because I can see the goal. Like the direction towards the goal is free for me to go. Well, in this case, we know it works. We can see it works. But on the previous example, we know that it doesn't always work. Like if you can, just seeing that there is a straight line towards the goal doesn't always actually guarantee that we can actually hit the goal. So bug one is going to be a bit more careful about this. And this is where we said that this is like the con of bug one, like this is the downside, which is that it's going to actually be a bit slower. But we will come back to this about how we can make it even better. But what we're going to do with bug one is say, well, okay, we're not actually going to stop here because like, even though we can see that we can walk towards the goal now, maybe this is not the best idea. Like maybe we will still mess ourselves over. So bug one is actually going to say, you know what? I can see the goal, but that's awesome. But I don't care. I am going to keep going around the obstacle. And bug one is actually going to keep on going and is going to complete an entire cycle of this obstacle. So this blue line is complete entire cycle. And to us, we know that this is probably not the best thing to be doing. And Mark will be going through in a moment how to make this even better. But the idea of bug one is that after we go through the entire cycle, we now know the entire boundary of this obstacle. We know what this entire obstacle looks like. And once we know what it exactly looks like, we also know the best place to continue from it. Like specifically, we know that out of all the places we've been to, this location right here was the closest to the goal. Right there was the closest to the goal. Like no, because every square we've been to, we know the coordinates of that square. We know the coordinates of the goal. So we can just compare the distances between our current locations and the goal, and we can find the closest location to the goal. Once we know the closest location to the goal, then by definition of what we said bug one was going to do, we're going to find the best location to continue towards the goal. Well, once we find that best location, we're going to go back towards it. So we're going to go back to that best location. So that's the purple here. We're going to go back to best location. And once we've gone back to the best location, we can continue with that original bright magenta step of walking towards the goal. And that is the fundamental idea of bug one. So I guess the question is this: do we think that this is guaranteed to actually always work? It doesn't matter whether it doesn't matter like how slow it is, and we'll come back to that in a moment. We'll actually do a quick analysis, not too formal. We'll just like briefly analyze how slow this thing can be. But at a high level, and I guess I'll just take some, if you have an opinion, you feel free to throw it in the chat. But I guess we'll start off with the yes, no of, do you think this is guaranteed to eventually hit the goal? Or do you think it will still eventually hit an infinite loop like bug zero does? So do you think it will work, or do you think it will fail? So take a moment, say a yes or a no in the chat. And Mark, do you want to let me know what everyone is thinking? All right, we have,
Seems like they think it will work.
we have a lot of people who think it's going to work. And yes, that is definitely correct. And so if you're not sure why, I'm going to go through a very informal argument, sort of just as, I guess, a mini proof. I guess this isn't a very, like Battlecode isn't supposed to be a very proofy mathy class, but for the sake of things, I always think that it's good to believe the algorithms that you're going to implement, not necessarily be able to prove them formally, but you have to at least believe that they work. Like if you don't believe the algorithm, then we're not off to a good start. So I'm going to try to convince you, if you don't understand, if you don't think that I guess if it's not clear why this should always work, I think it would be useful for me to try to at least try to convince you, so that you can be confident that this algorithm actually does what I claim it does. So as a brief proof for why this actually always works, my claim is that each time you hit an obstacle, fundamental claim, let's pick a cool color for this. Let's say that my fundamental claim is that each time you leave an obstacle, you leave it, you are closer to the goal than when you first hit that obstacle. And that's the fundamental claim. And hopefully it is reasonably clear why this is true. And as like a brief explanation for this, well, you'll notice that what bug one is doing is that it's always picking the closest point to leave the obstacle. Like the point where you leave the obstacle is the point on the obstacle that is the absolute closest to the goal. So the only way for this claim to be false is if the point where you originally hit the obstacle was also the closest to the goal. But hopefully, and if you think about it a little bit, and this is something that I won't go into a detailed proof of, but hopefully, like if you think about it and draw a couple of pictures, it will be true. If the first time you hit an obstacle was at its closest point to the goal, then the obstacle shouldn't really have been in your way. Like, if you hit an obstacle, then like the whole reason it's an obstacle is that it's in your way. And if it's in your way, there should be somewhere else on the obstacle that is closer to the goal, which is where you're trying to go towards. So if you end up at a point on the obstacle, which is the absolute closest to the goal, then the obstacle should be behind you instead of forward and in your way, if that sort of makes sense. So the main thing I'm trying to say here is that you really shouldn't be hitting the obstacle here. Like, it doesn't really make sense to be hitting the obstacle right here, because if you're hitting it right here, then the obstacle is behind you. It's not in front of you. It's not in your way. So it's not actually an obstacle. If you reach the obstacle at its closest point to the goal, then actually the obstacle is behind you, and it's not even an obstacle at all. And so because of that, what we're saying is that every time you leave an obstacle, you're leaving it from a different place that you first entered it. And because you're leaving it from a different place than you first entered it, you're going to actually end up leaving it closer to the goal than when you first hit that obstacle. Now, the key thing about that is, what this means is you can never hit an obstacle twice. What this means is that you can never hit an obstacle twice. Or like, you can never hit it more than once. Because when you hit an obstacle, you're going to, by the time you leave it, you're closer to the goal than when you entered it. And when you're not on an obstacle, then you're always on this magenta path here, this big magenta path here, or here, or here. And in that path, you're also walking directly towards the goal. So what this means is you're always getting closer and closer to the goal. So if you're always getting closer and closer to the goal, then it doesn't make sense for you to somehow end up hitting that obstacle again. Because if you hit it again, then you have to sort of like gone back on yourself at some point. So if you're always getting closer and closer to the goal, you can never hit an obstacle more than once. And you can notice that by now, we already have something that has a cooler property than bug zero. Because bug zero, you'll remember, on this example, would go around this obstacle, it would leave it, and then it'd come back and hit this obstacle again. And then it would go around again, and then it'd leave it, and then come around again. And so this bug zero actually ends up hitting this obstacle infinitely many times, because it'll just keep on going around and around and around. And this is what bug one solves. Bug one never hits an obstacle more than once. And so the guarantee of bug one is that if there are less than infinity obstacles, then we should also use less than infinity time to hit the goal. Because at worst, we will hit every obstacle, and that's the worst we could do. And so obviously in the Battlecode world, there are hopefully going to be less than infinity obstacles. Our anomalies don't work so badly that you will have infinity obstacles in your way, hopefully. And so if you use bug one, you can actually guarantee that even if it does some slow things like going around the entire obstacle, you know that at least it won't take infinite time to get the goal. In other words, it will eventually hit the goal. In fact, if you want something a bit more rigorous in terms of an analysis of its actual amount of time, so like actual amount of time, you can actually check that, well, if we think about what's actually happening here, in the worst case, what we have is along every obstacle, well, every obstacle we hit, for every obstacle we hit, we have to go around it entirely. And if we go around it entirely, let's suppose the obstacle, let's say it has perimeter P. So if it has perimeter P, then going around it entirely is going to cost us P p amount of walking. And then we also have to go back to the closest point. Now, it turns out that going back to the closest point, well, definitely, we can say that it costs at most p, because at the worst, we'll just have to go around the entire thing. At worst, we will just have to go around the entire obstacle again to get back to our closest point. If you think about it a bit more, though, there's actually two ways to get to the closest point. You could either go the purple way, which is on this diagram here. You could also go the other way. So there's actually two choices for how you get to the best location. And so if you always pick the shorter one of those two, so if you remember which way was the shortest one, then you can actually guarantee that, well, let's say if the best location was closer going clockwise, then you always go clockwise. If it was closer going counterclockwise, then you always go counterclockwise. So you remember which way it was. If you're able to remember that, then you can actually have this to p over 2. And so you actually end up spending a total time of 1.5 p time, 1.5 p per obstacle. So your total time is actually bounded by the distance to goal, using something like, if you did like rc.distance squared to, so like, like map location.distance squared to, so sort of like the direct mapped distance. And then plus 1.5 times the perimeters of your obstacles. But that would be sort of like a bound that we can have on the amount of time you spend on doing something like bug 1. Now, we know that bug 1 has some things that it does that are not so good. Like, we can still look at this picture and say, why are you going around the entire obstacle when you're literally already closer to the goal? And that's a great question. It's a good question to be asking, because that's going to lead us to bug 2, which Mark is going to now talk about.
Hello. Okay, let me get my board back.
All right. If you have any, if you have any questions about bug 1, feel free to drop them in the chat, and I will answer them as we go.
Yeah. So the key takeaway from what Jerry said is that walking around the target allows us to get closer and closer to it. So the whole point is that if every time I leave an obstacle, I'm closer to my target, then that's good. So I don't have to necessarily find the closest point. I can just, as long as I leave closer, that's okay. So one thing that I can do to keep a reference is, if I'm here, I'm going here, I can remember the line connecting the 2 points. And then I want to keep getting closer along that line, essentially. So what happens is I walk through that line, and then I see my obstacle. And then I do exactly what bug 1 does. So I go around, and then I'm in that line again. So what I can do is I can just follow that line back. I don't need to go through the whole thing, because now I know that I'll be leaving this obstacle closer. Now, this might sound exactly like bug 0 at this point, but there are two key differences. The first difference is that I have a direction. I have like one reference line in mind that I'm trying to progress through. So that's different than just walking towards the target the moment I could walk towards the target. The second key difference is that I only take that line when I'm closer in that line to what I've ever been before. So for instance, if we go back to the original example that was bad for bug 0, which looked something like this, and say my bug is here. So my reference line looks something like this. My bug goes through the reference line and then hits the obstacle. It goes this way. And now it sees the line again. Say that the obstacle is a little bit wider here. So then now it's closer across that line, so it can move back across that line. And now it's here. And now it explores back. It is back where it started here, but it's not closer than it was before. Like it already knows that it was here as that was the closest point. So it keeps exploring the obstacle. And then now it's kind of like bug 1, but it's kind of slower. So what it does is it's sort of like bug 1 is good in the sense that it has guarantees, but it could be slower in like average cases, which is not ideal. Bug 0, it works in average cases, but it can be stuck in an infinite loop in like contrived examples. So bug 2 kind of gets the best of the two worlds. It does not get stuck in an infinite loop, and it's kind of faster in an average situation. I think that's it for the theoretical part of this lecture. Jerry will now implement a simple example of bug 0, and yeah.
Cool. I'm also going to just quickly show some color images of these diagrams, just in case the color images might be helpful.
Yeah, definitely better than my drawing.
So the color, where did my share screen go? There we are. Cool. So the color images look like this. So for example, if we had on the top one, let's just look at the top one first. You had like the green is the start, the orange is your target, and then you'd have this pink reference line. And then what the idea of bug 2 is, well, instead of going, it's sort of trading off the idea of bug 1, where bug 1 says, well, you have to find the best location to leave the obstacle. Bug 2 says, well, you don't have to be at the best location. You just have to be at some location that's like better than where you started off. Like it doesn't have to be the best one. And so one way you can measure what's better is by just checking against this straight line, this reference line. And so I'll just draw out the lines that I'll draw out like the paths that you'd end up taking. You would end up going around the obstacle. You'd hit this line again and you'd be like, well, I am now closer. So I can just leave the obstacle here. And then I hit another obstacle. And I'd go around again until I hit the line again. And then I can continue my merry way towards the goal. And similarly on this other example, where if we started at this green point, we would go forward, we'd hit the obstacle, we'd start going around. And note that even though you hit the line here again, you're a bit further away. You're further away than you started. And so we don't actually count this as really hitting the line. And you keep going until you do hit a point that is closer to the line. And then you can continue on your merry way. And so this is bug 2, as Mark showed. And it is actually quite good as well. And it definitely doesn't seem to do a lot of the sillier things that bug 1 does do. Cool. But what I am going to do now is I'm going to move on to sort of a coding session where we actually implement bug 0 together. And so we're going to actually take a look at what a real implementation of a bug algorithm will look like, so that you're able to sort of get a working one inside your code. So I'm going to go ahead and start up a new share with my terminal window, which is my fancy coding space. So if we're back on the lecture player, back in the lecture player, what's the word I'm looking for? Our scaffold has changed slightly since last time. The only changes I've made is that we've sort of, I think when we left off last time, we had an example funcs player copy. So we've just renamed that to now actually say lecture player, because this is the player that we have been creating together in lecture. And if you look here, the typing a bit faster than my computer can register, but we have example funcs player as well in this repo, and we've reset example funcs player to the original version of example funcs player. So it's the absolute original. But cool. So what we're going to do is we're going to come back into lecture player, and we're going to actually start writing out a pathing algorithm. So we'll notice what we're going to notice is that there are some functions, some of our strategies have target locations. And with these target locations, what we're saying is that, well, we actually want to reach these targets. But what we're doing right now is we're simply just moving in the direction 2. Now, this definitely works. It is guaranteed to get us at the goal, but we could hit a situation where perhaps this straight line is filled with 100 rubble squares. And if we just take this straight line, we're just going to walk through all of that rubble and perhaps take 10 times as much time as we could have had by just going around that rubble. So what we're going to do is we're going to implement bug zero as a way to get around this. So what we're going to do is a new file to powding.java. So we're going to put all of our powding code inside this new file. So it's going to be package lecture player. Copy this stuff from the top because it's easier that way. Random. Cool. For our, no, it's not minor strategy, we're going to be having powding here. Okay, cool. So this is going to be a powding algorithm. And the idea of powding is what we're going to do is we're going to have a big fundamental function, which is going to be a, which is what it's going to say. It's going to say static void. And we're going to say walk towards map location target. And what walk towards is going to do is it's going to actually, well, it's going to do what it says it does. It's going to take our robot, which is where it currently is, and then take us towards that map location. We're also going to take a robot controller because we're going to need that to be able to, well, I guess, actually control our robot. Cool. So the question is, well, how are we actually going to walk towards that target? So I guess the first thing we have to do is know where we are. So map location, current location, is our location. Good thing to know where you currently are. If you don't know where you currently are, there's not much we can actually talk about. Cool. So we're going to have map location, current location. So once we know our current location, we know the direction that we would like to go in. So we're going to say direction D is current location dot direction to the target. So if we're already in, so what we're going to do is we're going to so direction D is going to be the direction that we would like to go in. So it's going to be the direction that we would like to go in. Now, there's one thing that we should add in the front here, just to be absolutely careful, which is that, well, if the current location is equal to the target, if it's equal to the target, then we're actually already done. There's nothing we have to do because we're already actually at the target. So there is no walking that we have to do. Be very careful that when I wrote this, I did not write if current location is equals to target like this. This is bad. The reason this is bad was exactly what we covered in the Intro to Java lecture, which was the lecture 2 for why. We've talked about why this is a really bad thing to write and it will not actually work. So be careful here that you actually write if the current location dot equals target. So we're going to have direction D is the direction that we're actually wanting to move to go towards the target. So first thing we're going to do is if rc.isMoveReady. Move ready is movement ready. It's a great question. I'm not actually sure what we called it. So I'm just going to take a quick moment to look it up on our trusty Java docs. A moment while I look up on the Java docs. So the Java docs are a great resource to actually check the functions that exist and the ones that you can call. So you go to your Java docs to check which functions are available. So is movement ready? Is a call. Is movement ready? So this checks if our cooldown is ready to move. And if it's not, if our cooldown is not ready to move, then there's actually no point for us to even try doing anything. So let's actually move that right up to the top. If our cooldown is too high, then don't even bother. There is nothing we can do anyway. So only if our cooldown is actually low enough for us to even try to make a move, do we actually consider it. And so just a reminder here that we're already at our goal. Either. Cool. So now that we have our direction, we can actually start thinking about what we want to do. Cool. So the first thing is we're going to say if we can actually already move in that direction, it's an available move. And we're going to say that if it's not an obstacle, is not obstacle. Let's actually say not is obstacle using RC of that location. So I'll just make a note here. We're going to implement this function later. Implement this. So we're going to say that this checks if moving the square we reach by moving in direction D is an obstacle. And we'll talk about what this means in a moment. So we're going to say private static boolean. So boolean, because we're returning a true or false, is obstacle. C direction D first game. Say return false for now. So if it's not an obstacle, then this is easy. We just move in that direction and we're done. Right? This is the easiest case of bug zero. The easiest case of bug zero is if we are not going to walk into an obstacle, then let's just walk straight towards the goal. And that's the easiest case of bug zero. The easiest case of bug zero. The harder case of bug zero, let's actually just note down what we did. So easy case of bug zero. No obstacle in the way. So let's just do it. Go straight for it. Else, hard case of bug zero. There is an obstacle in the way. So we're going to have to go around it. The question is, how do we go around this obstacle? The question is, how do we go around this obstacle? Now, this actually needs to take a little bit of thinking about, because what does it even mean to go around something? Like, how do you actually go around? Like, what does it mean to go around? Like, I think it's easy for us to reason about going around something because we can actually see the entire picture. We can see the entire picture. But if you're a bug on the screen, what does it mean to sort of like go around something? Especially if you have to reason about it in terms of, say, going north, going east, going west, going south. Like, if you're trying to, like, let's say there is an obstacle next to you right now. Is it like, if you're supposed to go around it, are you supposed to go west or east? Like, I think as a better example, let's draw a picture. Like, if there was an obstacle here, and you were here, and I just told you go around it. Do you go west or do you go east? You have two choices, and it's not immediately clear which one you should take. And I guess partly it also depends on what you've tried already. Like, I guess if we knew that what we've done so far in terms of trying to go around the obstacle was we've already gone like this, then the correct answer is, well, you should continue going east because, you know, you were going around the obstacle that way already. So if you were already going that way, you should continue going that way. But if what you've done so far goes like this, then you should go west. So there's like some other extra information we want to be keeping track of, right? Like, it's not like just knowing where the obstacle alone is doesn't actually tell us enough about what it even means to go around the obstacle. So we actually want to know a little bit more information. So this actually isn't enough. We need a bit more. So what else do we need? What we're actually going to track is we're going to call this private static bug direction. I'm going to start this off at null. Now, what bug direction is going to be? Bug direction is going to be the direction that we are trying to use to go around the obstacle. Bug direction is going to be the direction that we are trying to use to go around the obstacle. Okay, bug direction is going to be the direction we're going to be trying to use to go around the obstacle. The first thing to notice is that it starts off at null. And what we're going to say is that it is null if we are not trying to go around an obstacle. So if we're not actually trying to do anything, a bug direction is going to be null. And it's only going to be set to a direction if we're actually trying to go around something. So the first thing we have to do is here at 31, because there is no obstacle in the way, we have to make sure that we reset it to null. Because the first thing that we're going to say here is that, well, if we don't have a direction that we're currently trying to use, so if bug direction is null, if it is null, then we are actually going to initialize it to the direction that we would like to move in. If we don't know what we're trying to do, make something up. And what better than to pick as the direction we want the best direction towards the goal. If we have to pick a direction to go in, what better than to pick the direction that takes us toward the goal? So the first thing we're going to say is, well, if the bug direction, if we haven't set it yet, we're going to set it to the direction D, which we defined here, which is the direction that takes us towards the goal. Cool. So we have that. So finally, the last thing that has to happen is we actually now try to actually go around the obstacle using bug direction. So how do we go around the obstacle using bug direction? Well, it would sort of look like this, right? I'm going to say, well, if we can move in the bug direction, and I guess if we can move in that direction, and if it's not an obstacle, RC bug direction. If it's not an obstacle, then we can RC dot move in that direction. Right? If it's not a problem, then we can just move in that direction. All right. So ignoring the is obstacle code that we haven't written yet at the bottom, who thinks this code works and who thinks there's something missing? We're going to give a couple moments for people to say something in the chat, whether the answer is yay, we think this works, or no, there's something missing, or if there's a question like, I don't understand what's happening. Like, what is bug direction? What's going on here? So take a moment, drop your thoughts in the chat. What do you think is happening in this code? Is it going to work? Is it going to fail? What's going to happen?
People are saying that you did not change the direction, so we will not.
Yes, exactly. That's exactly what we're missing in this code. We have tried to pick a bug direction to go around the obstacle, except this go around thing never really happened. We just picked the direction that we wanted to go forward in, and then we just tried to go forward into the obstacle anyway. So this is not a really good thing to do. That's exactly what we are missing. So what we're going to do is we're going to notice that, well, since we haven't actually tried to fix the direction we're going to go in, let's do that. So what we're going to notice is that, well, if this move succeeds, then we're happy. The chances are it might not succeed. Chances are it might not succeed. Now we have to think about what to do if that move fails. So if that move fails, it means that the bug direction is taking us straight into the obstacle right now. So we should start trying to turn around. And the strategy we're going to use is, imagine if you were a bug sitting on the screen and you were trying to go around an obstacle. Now, I think as humans, it's easy to think about an obstacle, going around an obstacle is actually just, well, like you just follow it. But let's sort of like break that down a little bit more. I think a really nice way to think about what it means to go around an obstacle is, imagine if you held out your right hand. You held out your right hand and you said, okay, I'm going to just hold out my right hand like this. Just hold it out. And I'm just going to walk forward with my right hand always on the obstacle. I'm going to walk forwards with my right hand always on the obstacle. Or you could think of it the other way. You could think of it as, I'm going to walk forward with my left hand always on the obstacle, right? And that's the idea. I'm going to say, as long as I can keep one of my hands on the obstacle, as long as one of my hands is always on it, and I just keep going forward, then that sort of is like an intuitive way of describing what it means to go around it. Like as long as your hand is always on the obstacle, then it sort of makes sense that we're going around it. So if you keep going forwards, as long as your hand is on the obstacle. And that's exactly what we're going to do. I think we're going to do it with the left hand on the obstacle. So what we're going to say is, if this works, we're great. But if this doesn't work, we're going to say, I'll come back to that. If this doesn't work, if this doesn't work, what we're going to do is we're going to just say, well, I can't go forwards. So if I can't go forwards, that means the obstacle is in my way in front. And so if I'm keeping my left hand on the obstacle and the obstacle is in front of me, I should turn right. Yeah, so let's just take a moment to think about that. If I'm trying to go around the obstacle, and the way I'm doing that is I'm going to hold my left hand always on the obstacle. So my left hand is always going to be on the obstacle. And if my left hand is always going to be on it, and the obstacle is right in front of me right now, so the direction I'm trying to walk in is going to take me into the obstacle, then I should turn right. Because by turning right, my left hand is going to like start sweeping around this corner or whatever it is that takes my left hand onto the obstacle that I was about to walk straight into. So I'm going to turn right. So if I'm about to move into something, I should turn right to keep my left hand on the obstacle. So what I'm going to do is I'm going to take bug direction is bug direction. So I'll rotate right. And finally, I'm going to just take that. I'm going to wrap it inside a loop. And I'm going to wrap it inside a loop to happen 8 times. And I'm going to do this 8 times to try all 8 possible directions. Because as soon as we find a direction that works, we're going to break out of this loop. It's sort of like saying, well, if I manage to try all 8 directions, then essentially I'm actually stuck right now. If I have to try 4 directions, then it's like I've walked into a dead end and I've done like a U-turn and I've turned around and started walking back out and my hand is on like the other side of the wall. But most of the time, like if you walk into an obstacle, you might actually need 1 or 2 iterations of this loop to sort of like turn around a bend or something. But the idea here is what we're going to say is we're going to be walking forward. And then if we hit an obstacle, we're going to turn right to keep our left hand on the obstacle. There's actually one more missing thing here. We're not actually done yet. There's one more missing thing here. It actually goes here. Does anyone know what's missing actually? Are there any suggestions for what we should insert in here? Actually, it doesn't go there. It goes there. No, that's not that. It goes there. Okay, what are we missing? Do we have any ideas? Mark, what does the world think of what might be missing here?
The world has nothing to say.
The world has nothing to say. Okay.
Oh, we're not checking relative distance. Do we need to know? That's for bug 1, right?
Bug zero, it actually doesn't check the distance. Bug 0 is just one that says follow the obstacle, and once you get out of the obstacle, you're done. Okay, let's draw an example. Let's draw an example together, and this will show you. This will give a good picture of what's missing. Suppose we're going around an obstacle. Oh dear, ASCII art. This is gonna go great. Suppose we're going around an obstacle. All right. So suppose we're going around an obstacle. We're currently here, and we've just gone up like this. We've just gone up, and we're currently here. Right? We're still going upwards, and like let's use an O for our current location, and then let's just mark this out with X's to say that this is all obstacle. Cool. So we've just been going up. And then let's just play this algorithm out and see what happens. Let's just play it out together. All right. So the first thing that's going to happen is we're going to say, okay, we're going to check. So the bug direction is pointing upwards, right? The bug direction is pointing north, which is great. Bug direction is north because that's the direction we're currently going. And we're going to come here. We're going to say, well, can we move north? And is there an obstacle to north? And the answer is we can move to the north. There's no obstacle there. Everything is clear, which is great. So we're going to move north. So we're going to move upwards here, and we're now here. Awesome. And then on our next turn, we're going to get to this code again. And then we're going to say, well, can we move north? The answer is true. Is there an obstacle to the north? There's no obstacle to the north. So we're going to do that again. So we're going to end up here, which is great. And then we're going to, on our next turn, we're going to get here again. The question is, can we move north? The answer is can. We can. Is there an obstacle there? No, there isn't. So we're going to do that again. And then so on. So you'll see that eventually we'll hit a problem where we're actually just going to keep on going northward like this, which is actually not going around the obstacle at all. So we've actually just, so bug 0 has just lied. Well, this code is a lie. It is not implementing bug 0 because we said we wanted to go around this obstacle. So what we just ended up doing was we just shot straight off northwards into the abyss or wherever the other anomalies go. So we've actually got something missing from this code. What's actually missing from this code is we need to turn around the corner. So this thing here on line 52 tells us that, well, if we're walking into an obstacle, so this sort of like handles like when the obstacle is curving out into us. When the obstacle is curving into our path, this helps us turn around it. But we haven't handled the case where the obstacle turns away from us. And if the obstacle turns away from us, we should actually follow it in. Like what we wanted was for us to eventually go around this way. So what we're going to say is we're actually going to just set a bug direction to rotate left here. So we're going to just try to turn left whenever possible. We're going to try to turn left whenever possible. Whenever we're allowed to turn left, we should do it because it will keep us going towards, keep our left hand on the obstacle. But then if we but this is okay to have here, like even if this points us in a direction that's illegal, then we'll just do an extra loop around here and rotate right again next turn. But the idea is that having this rotate left here makes sure that we're actually always turning back into the, turning back with our left hand on the obstacle. And that was the last thing we're missing there. So this is what, this code here is what I believe, given that it compiles at least, it's sort of coding this live, but given that this code compiles, this should be a successful bug 0 implementation. The last thing we have to actually discuss is what it means for something to even be an obstacle. And so in this case, well, we haven't actually talked about this much yet, but I guess what we want to think about is, well, I guess if we think about it, well, the whole point of implementing bug was to avoid those squares that had lots of rubble, right? We wanted to avoid those squares that had lots of rubble. So a simple thing we can do is we can say, well, we're going to say map location, adjacent location is rc.getLocation, which is our current location, dot add that new adjacent location that we're going to be ending up on. I'm going to get that adjacent location. And we're going to say, well, we're actually going to say, no, we're not. We're just going to say, well, on that adjacent location, we're going to say int rubble on location is rc.sense rubble adjacent location. All right, we're going to sense how much rubble is there. Because once we know the amount of rubble is there, we can say, one thing we can do is we can say private static final int. So final int is going to give us a constant. As a simple one, we can say acceptable rubble. Acceptable rubble is, I'm just going to pick a number for now. Let's say 25. And we're going to say any square with any location with less than or equal to this amount of rubble is not an obstacle. All other squares are obstacles. Say, well, if that's the acceptable rubble, we're going to turn that rubble on location. We're checking, is this an obstacle? And so it is an obstacle if this is greater than the acceptable amount. This is an obstacle if the rubble on that location is greater than the acceptable amount of rubble. Cool. The last thing we have to do is just take this code and plonk it into everywhere that we actually need pathing. So in the minor strategy, we had this target location. So instead of using toMove, what we're going to do is we're going to say, what happened to the tabbing here? All right, we have tab space 2. Okay, we're going to say, well, if the target location is not null, then instead we're going to say pathing walk towards RC to target location. That's going to be what we're going to do instead. The target location is not null. We're going to do pathing walk towards the target location. The other thing we have to do is, where else do we do pathing? I don't know, where else do we do pathing? No movements here. The builder is, what is this? This appears to also be moving towards a target location. So let's say instead of direction dir, let's say map location. Target location is null. And so instead of keeping the direction, we can say target location is going to be, instead of RC get location direction to, we're just going to say remote get location. Get rid of that. If direction is, so if the target location is not null, then we can do pathing move towards nope, it's walk towards that target location. Cool. Let's just check that check if there's anywhere else where we have to do intelligent pathing. Can move explorer. I think that's exploration, so we don't want to mess with exploration. This is our pathing code. This is a random move. So, moment of truth. Does this code compile? And I will surely hope that it does. All right, let's see if this code compiles. Oh dear, it doesn't. This is quite a disaster. Let's take a look at what made this code not compile. This is all in builder strategy, which is quite curious. So let's take a look what happened in builder strategy. Builder strategy, line 31. What's happening here? Target location. Oh, I can't spell. Target location. Let's give this another try. There wasn't incompatible types, which I just take a look at. That's on the line 42. Application direction. Direction. Oh, that should be direction. So let's give that another try. All right, that's successfully built. There is a new update available, so let me just update that. Cool. And nope, let's not run this amazing bot called Jerry Player. Let's run Lecture Player against the example funds player. Let's run it on intersection just to see how it does. So that's going to take some time to run. But that, as a summary, so while that runs in the background, this, again, is the implementation of bug 0. And we'll just double check that this works in the replay once the match finishes running. But this is the implementation of bug 0. We will be pushing this to GitHub after the lecture. So this will go into the lecture player repository where everything else has been going. So this will be up after lecture. In the meantime, while we wait for that game to run, a couple of announcements. So things to mention while we wait. I can think of it as some things to mention. So first of all, don't forget that I guess first of all, today is Friday, so we obviously won't be having a lecture the next 2 days. Nevertheless, if you have any questions about anything, feel free to reach out on Discord. We will exist in some capacity and try our best to answer any questions you have or fix any issues you might have. So obviously no lecture the next 2 days, but we will exist in some capacity. Other than that, Monday, if you check your syllabus, Monday is actually going to be an office hours day. So there is no formal lecture scheduled for the coming Monday next week. However, we will be present on Discord. We will have full office hours on Discord in the lectures channel. If you have any questions you would like us to help with, or anything else about any of the lectures, any of the setup, any code debugging, anything you'd like to talk about, we will be on Discord on Monday. Additionally, Monday will be the submission deadline for our first tournament. So on Monday, we will be having the sprint tournament. Sprint tournament will be on the Tuesday next week, but Monday is the submission deadline. So remember to get in your bot submissions by 7 p.m. Eastern time on Monday. So you can submit through the competitor dashboard at play.battlecode.org in the submissions tab. So make sure you get in your submissions there by 7 p.m. to be entered into the sprint tournament. If you're a 4-credit student, it is not strictly required. However, it is an opportunity to have a stab at winning a prize. So just again, the sprint tournament will be happening on Tuesday. So remember to get in your bot submission by Monday. So sort of the key announcements there were that we'll be having the office hours instead of standard lecture on the Monday. Tuesday, we will be streaming the sprint tournament games during lecture time. And then we will continue with our lecture series on the Wednesday with communication strategies. But other than that, do not forget to get in your bot by Monday. All right, that match has completed. And so lecture player has won by having more archons. I'm going to try to figure out how to bring up a client. So let's say /client /Battlecode client. I'm going to move my share screen over to the client. It's now versioned, which has now been upgraded to 2022. Move to the queue. We're going to upload that replay file we just generated, which is, I think it's this one. No, it might not be. I think it's this one. Is it this one? Example fonts versus lecture player on intersection, which was modified a couple minutes ago. So this looks like the right one. Cool. Created, modified just then. That's the one. Cool. So let's play that and see how it does. So lecture player is the blue one. And you see that blue one paths directly towards the goal. And you can see that although they are getting stuck there, that's because they don't actually see where they're going, and that's part of the exploration series. But when they are trying to go across, let's see if there are any examples of them trying to path across. I'm not sure that this is a challenging pathing map actually, but we would hopefully see in some instances that we do have some successful instances of padding. But we do see that we are able to successfully have our blue bot drain those lead squares. So that's, once again, that is the bug0 algorithm. I'm going to tie off with what we know is from what we learned yesterday with our Git lecture. So we're going to get status to see how much code we've edited. We're going to add this source because that's what we have changed. We can check our status to check that this is indeed the changes that we're going to commit. Let's actually add the version.txt in as well, even though it doesn't necessarily matter too much. But this is what we are going to commit. If you're interested in double checking what you have staged, you can actually use Git Diff Stage. It's a cool command you can use to sort of just double check. These are the changes that you're going to do, and you can see, well, this looks like what I want to do. So I'm going to commit that at bug0 padding code and at bug0 padding code. That creates the commit. So -m lets you put your commit message on the line, and I'm going to push that to main. Cool. So that being that, there's one last thing I want to mention before we wrap up for today, which is that you will have noticed that in our bug code, we made one significant simplifying assumption, which is that that code is still open somewhere, which is that we did this is obstacle in a quite a very simple way. Our is obstacle simply checks it against a flat threshold of 25. And we're saying that, well, if it's more than 25, we never want to touch that square. And if it's less than 25, we always want to touch that square. Now, this is actually not necessarily a really good idea. And this will be something that you might be interested in playing around with. So the two things I want to mention are that, well, firstly, you may be interested in thinking about how you can make this acceptable rubble threshold something more useful for you. For example, on some maps, perhaps all of the squares have really low rubble, far less than 25. And in that case, your acceptable rubble threshold might be too low, might be too high. On other maps, maybe there is a lot of rubble everywhere, and perhaps you need your rubble threshold to be lower. Like if everything is rubble, if everything is rubble, then maybe you have to adjust your threshold. So sort of like maybe this threshold should depend on what you see on the map instead of just being a fixed 25. So it will be an interesting idea for you to think about how you can adjust this threshold, this acceptable rubble threshold, depending on what you actually see. And so if you can adjust that, perhaps you can get a bot that is more able to adapt to its surroundings. So that's the first thing I want to mention. And the second thing I want to mention is if you're actually able to do that successfully, bug0 might not actually encounter too many of the issues that we mentioned in that we mentioned earlier at the start of the lecture. So sort of like with bug0 being bugged and not always working, if you're able to sort of like adjust that successfully, you might even be able to come up with a bot that is able to sort of like overcome obstacles that do appear pathological in strange shapes like that, but use bug0 to sort of like automatically adjust that rubble threshold to still be able to get past it. And so you sort of really have two choices here from how you want to sort of improve this padding algorithm. So your two choices really are, well, they're not even two independent choices. You could sort of like do both of them if you want. But like a simple change, the first simple change I would recommend you really try to investigate from here is how to adjust this acceptable rubble threshold. I think being able to adjust this cleverly will do lots of improvements for your bot. And secondly, I think this is something, if you really have the time to invest in it, because I think implementing it will definitely be a lot more challenging, is to perhaps have a shot at bug 1 or 2. They will be harder, but I have a sense that bug0, even without bug 1 and 2 features, actually does really well already. So it's up to you what you really want to do from here. But these are some of the recommendations that I might suggest. Other than that, that's all we really have for today. So if there's Mark, if there's any last questions in the chat, please let me know. But otherwise, good luck to everyone for the sprint tournament. And we're looking forward to seeing everyone next week and on Discord.
Yeah, nothing is going on in the chat. Thanks for joining us, everybody.
Sounds great. Thanks so much. Good luck and see you around.